So, we are going to be talking about energy. Energy, though, is not how the chapter really starts this. Rather, the chapter does start about energy, but then it kind of waves its hands and gives up trying to give a definition of it, and then it kind of just suddenly gives an equation for kinetic energy, but no explanation where it comes from, just some magic equation, and then it starts talking about work. And so what I'm going to do is I'm going to start with work because that's really how the idea came about. So work, you have an object here, you exert a force on it, and you want to know, well, what are you doing to make the object move? You're exerting a force. And how do you know that your force is doing anything? Well, you see it move. Okay. And so Thomas Young introduces the concept of energy, which comes from the Greek for activity, really, and so it's an idea that you're making it move, so you're doing something to it. So you're adding some kind of work to it, and so the work became the effect of the force. And so Young's original idea here would be that force times the distance it moved would be equal to the work. Okay. So we're going to expand on that later because that turns out to be a very simplistic sort of concept right there. So we look at it and we say, well, okay, so we do work on something. What are the units of work? Well, if work is force times distance, that's going to be newtons times meter. So Newton is a kilogram meter per second squared times meter. So this is a kilogram meter squared per second squared. And we call that a joule, after James Joule, who worked worked a lot with energy. And so James Joule's name is now applied to this unit. This is the SI unit of work or energy. Well, often, I talk kilograms moving at meters per second squared. That's a fair bit of force going in there. And so sometimes what you do is you say, well, sometimes you have small objects moving and they're not moving very fast. So often in the laboratory, when we set up and do experiments with energy, we have things that are only a few grams across, and they're moving at centimeter per second squared, so you can actually watch them move across the table, without suddenly slamming into the far end of it in a fraction of a second. And so we have gram centimeter squared per second squared, and this is an alternate unit of energy that we call an erg. Which actually comes from the Greek for activity or energy. And so an erg. Now, if you look at it, there's 1,000 grams in a kilogram. There's 100 centimeters in a meter. So 100 squared, 100 squared is 10,000. So 1,000 times 10,000 is 10 million. So you would say that there's 10 to the 7 ergs in 1 joule. So let's explain this. That means an erg is not a whole lot of energy. What are we talking about with an erg? Well, an erg or two, just a very few ergs, that's the amount of energy it takes to pull an electron off of an atom. So when we're talking ergs, we're talking typically very small amounts of energy, and so that's kind of in the range of what an erg would be. A joule is actually a fairly decent amount of energy, and so a joule would be like the amount of energy it takes to lift a bowling ball off the ground and set it on a very high rack or something. And so that would be like a joule or two or three or whatever. So we're talking joules at that point. So kind of gives you a mental idea as to an erg and a joule. But that's the kind of the basic right there of energy. And so next we'll go ahead and do a couple of examples.